Okay, notice on problem 7, the domain is real numbers. And it's kind of weird looking because it has two inequality signs, and you may not have seen this before. We are still trying to get x by itself. It's not going to move from where it is. It's kind of like we're still thinking leave x where it is. Notice that the domain is all real numbers. That means that anything we get, as long as it's not some, imaginary number, square root of a negative number, or like some fraction that's undefined, we're going to count it as an answer. When we get done, we're going to graph it on a number line. Excuse the background noise. It's just I got to do what I got to do to get these made, or we're just not going to have videos just because I'm having a hard time finding time to do it. All right, so if I want x by itself, here it is in the middle. It has a minus 5 with it. I could get x by itself by adding 5 to minus 5, and that would make it add up to 0, and x plus 0 would just be x. But if I do it there, I got to do it to all, there's 3 places I have to do it. I have to do it there, I have to do it here, and I have to do it here. I like these kind because to me they're the easiest inequalities of the more complicated ones. So now that adds up to 0, and now I have x minus 0, which is just x. I'm not even going to write the 0 in. And then I just go clean up the other 2 places. Negative 6 plus 5 is negative 1. 2 plus 5 is 7. And so there's my answer. It means my x's have 2 boundary values. I have negative 1. We'll put a negative 2 here, and then I'll put a negative 1. And then 0, 1, 2, 3, 4, 6. I really need to go at least up to 8 here. All right, so one boundary value is at negative 1. I'm going to circle it. I'm not going to color it in because there is no equal sign under that sign there. I call these a sandwich inequality because what this is telling me is all my x's are bigger than negative 1. So I'm going to shade with 2 colors here. My final answer I'll use a third color for. That means x's that are bigger than negative 1 will fit, but I have another restriction. I have a second one, and it is that all my x's have to be less than or equal to 7. So I kind of am covering up. I'm looking at x greater than negative 1, and I'm looking at x less than or equal to 7. So 7 is another boundary value. Because there's a line under it, I'm going to color 7 in. It means count 7 as an answer, but I want x's to be less than 7. So that would be like going all this way. So I have 2 things. Where do these 2 solution sets overlap? They overlap here. So I'm going to color in yellow over what I've written, what the solution set is. I would say anything bigger than, both of these things have to be true at the same time. Anything bigger than negative 1 counts, but not bigger than negative 1. But it can't get over 7. It can be 7, so we're going to count 7. So the yellow is actually my answer shaded in. You write your answer in numbers like this that I just circled. That's called a sandwich. I call it a sandwich inequality. And then you shade them in like that. Okay, we are going to see some problems that look a little bit different with inequalities, and we just have to kind of know that we're always trying to get x by itself. And we're going to look at how we would write these solutions. Number 9, again, is over all real numbers, and most of the time when we do things, they are over real numbers, and we just don't even bother saying it. We just go, okay. We don't even talk about the domain, and when we don't talk about it, we're assuming it's real numbers, but they're still stating it here just to kind of get used to that idea. If I want to get x by itself, I've got 2 separate problems here to solve, okay? Either one will work, okay? It's not like they both have to be true at the same time, because or means the first one can be true or the second one can be true. They don't have to both be true like the sandwich inequality that we just had. All right, so on this first equation, if I'm solving for x, all I got to do is subtract 3 from both sides. X is greater than or equal to negative 1. So if I'm going to graph that, I'm going to wait just a minute to graph it because I don't ever know like how high I have to go until I get the other one done. So that's one solution, okay, or one set of solutions. It's actually a whole lot of different numbers. Anything bigger than or equal to negative 1. If I'm going to solve for this x, I'm going to subtract 3. I'm going to get x is less than negative 10. Okay, so I'm glad I waited to shade it in because now I need like a negative 11 at least. Negative 10, negative 9, negative 8. I'm going to skip numbers here. Negative 7, negative 6, negative 5, negative 4, negative 3, negative 2, negative 1. 0 will be here. This would be 1. That would be 2. Okay, so I'm just going to shade in black and white here. X can be bigger than or equal to negative 1. So here's negative 1, looking at this one that I circled in black. I'm going to count negative 1 as a solution because there is a line under the inequality. And I am going to shade the numbers that are bigger than negative 1. 1 is bigger than negative 1, so I'm going to go in that direction. I can just kind of pick a number and say, is this the direction I want to shade in or not? Now, so anything over there is a solution. And at the same time, I got another whole set of solutions over here. X is less than negative 10. So negative 10 is a boundary value. I don't want to count negative 10 because there is no line under that. That line means it could be equal to negative 10, and it's not there. So we're going to circle negative 10, and not going to count it, so I'm not going to shade it in. And I want numbers less than negative 10. Well, negative 11 is less than negative 10. Remember, with less than, you're always going to the left on the number line. So my solutions could be anywhere that I see shading or a colored-in dot on this graph. That's how you would do number 9. Okay, on number 17, x is greater than or equal to 2. What I'm saying is that I've got some starting point, and I want all my distances from the starting point to be more than 2 away from the starting point. So you can kind of imagine if your starting point were here, you wouldn't want to count anything unless it was 2 units away. So here's, let's say that's my starting point. Let me mark it with a different color, maybe red. Like this would work. That's bigger than or equal to 2 away from it in a distance. But I could also, remember when we're talking about distance, and we know we're talking about distance because there's an absolute value. I'm talking about something that's 2 units away on the other side. So on the other side, 2 units away, and remember we're going to count that because there is a line under there. I'm going to make that blue. 2 units away would be right here, and if I want to be more than 2 units away from my starting point, which I use that line for, it would be like anything out this way would be more than 2 away. So, how I represent that's the idea behind this, okay? How I represent that is I would say, okay, whatever's inside of here, and we're going to have other things, other expressions, not just x in a minute. X is greater than or equal to 2. You copy it down just the way you see it, but then at the same time, it could also be more than 2 away the other distance. So what you have to do when you see the absolute value of x is greater than 2, it means the distance is bigger than 2. So think of the absolute value sign, just read it. When you see it, say, well, my distance is bigger than or equal to 2 units away. Actually use the word distance, and that can help you keep it straight. So I'm going to write my x down, but to talk about this blue part down here, the other directions, I'm going to have to, it's kind of like multiplying by negative in a way if you think about it. We would flip the inequality sign, and we would put a negative 2 here, because if this were 0, this would be 1 and 2. This would be negative 1 and negative 2. This is what I would actually write as my solution if I break it apart. And that graph up there is actually my graph of this situation that 17 represents. But let's do one that has something in the 19. Well, let me do one like that one. Let me choose 21. It says 2x plus 5 is greater than 9. The distance is bigger than 9 units away from a starting point, some starting point. Okay. So how do I do this? I take whatever's on the inside, and I say, okay, that's kind of my distance. If that distance is going to be bigger than 9 away if I'm going to the right, but if I'm going to the left, it's going to be less than negative 9 away. Well, what was this distance inside? How did they represent it? They represented it with x plus 5. So if you look, I'm kind of copying it down without the absolute value signs for the first equation. And then on the second equation, it's like multiplying by negative 1. I switch the direction of the inequality sign, and I changed the 9 to a -9. So now I can solve. On the first one, if I get x by itself, x is greater than -4. And on the second one, if I get x by itself, x is less than -14. So if I want to draw this, I've got a pretty good range here, but I'm going to make a long number line. Let's say this is 0, -1, -2, -3, -4. I'll just, every once in a while, put a number, -5, -6, -7, -8, -9. This would be like -10, -11, -12, -13. Here's -14. I'll label it. -15. I'll put -16 here. Okay. So the first inequality says, and I'll do these in with colors. The first one, x is greater than -4. -4 is like right here. I am not going to color that dot in because there was no line underneath that inequality to say that it was equal to -4. Where the number's bigger than -4? Well, 0 is bigger than -4, so I'm going to shade in that direction. Okay? Now let's look at the second one over here. This x is less than -14. Where is -14? It is right here. We don't want to count -14 because, again, there was no line under that inequality sign. But I want the numbers less than -14. Well, -16 or -100 is less than -14. If I'm $14 in the hole, I still am further ahead than if I'm $100 in the hole. So we're going to shade in this direction over here. And this is a graph of our answers, and sometimes the graph helps us a little more than looking at, our algebraic answers. But here are my two answers here. It's this one or it's this one. Either one would work, and that's what the graph of my solutions look like.